Okay. Can you hear me? Yes. Okay, thank you for the invitation and for this opportunity to visit, well, to not visit South Africa, but at least to speak to all of you from Oxford about a work that we just put on the archive this morning, and it's part of an ongoing project, so I will try to summarize the general logic. So this is work in collaboration with Sakura Sheffer-Nameki and Yinan Wang, both at Oxford. And what this talk is generally about is about the so-called geometric engineering of superconformal quantum field theories in dimension less than 6 here, with 8 supercharges at singularities in string theory or M theory. So we have in those theories, then typically we have both a Coulomb branch and a Higgs branch on the Coulomb branch. So we have a conformal field theory, which has some Coulomb branch operators that can acquire VEV, and then the low energy dynamics is a bunch of photons and their partners, or we can have a Higgs branch, which can have some interesting degrees of freedom attached on top of free hypers. And both of those, I mean, any of those, many of those can be engineered in type 2B or type 2A string theory or in M theory, as we'll review. So in the first part of the talk, I will focus on 5D n=1 superconformal field theories, which arise in this picture as at canonical singularities in M theory. And in the second part of the talk, I will discuss similarly the superconformal field theories in 4 dimensions with n=2 supersymmetry that arise at the same singularity, but in type 2B. So here I put some of the seminal reference. Of course, this work, I mean, this kind of engineering was started in various papers by Witten, Morrison and Seiberg, in 4D by Katz, Clem, Waffa, and Chapperet and Waffa, and then many others. And of course, in recent years, in fact, the geometry engineering picture has kind of undergone a resurgence, and there's been many papers, many interesting work. Here I'm trying to cite some of the most relevant here. There will be, I mean, but I apologize if your work is not there. If it's not in our paper, though, which has many more citations, please email us. So the general question for today is if I fix a given singularity, which will be a threefold canonical singularity, well, let's first try to remember what do we know, and we will ask what do we know about both the 5D SCFTs and the 4D SCFT in M theory and type 2B, and then how are they related? So that's the general question. So I will start with a view from M theory, so focusing on the 5D physics, then the view from type 2B, focusing on the 4D physics, and then looking at how they can be related by going to their 3D reduction. And then I will discuss various examples of these pictures. And well, it leads to a bunch of interesting curiosities, I think, which we discuss, well, we will discuss, I think, in work in progress and to appear. But I will try to highlight the most interesting ones at this point. So in 5D, so we have 5D in M theory, but let me rewind a bit and just so we are on the same page, start with a little bit of history. About this concept of geometric engineering, which I guess started in that beautiful paper by Katz, Clem, and Waffa in '96, where the idea was to engineer 4D n=2 gauge theories directly from geometry. So this is by contrast with brane engineering when you have gauge theories because you have an open string sector. Here instead, what we have is a local threefold, like a local Calabi threefold, which looks like a local K3, so a resolved AD singularity fiber over a curve. And the shape of the AD fibers will give you an AD or E-type gauge group, where you have here like light W bosons that correspond to D2 branes wrapped on those fibers, and you take the fiber size very, very small and take the limit of the singularity, then you expect to recover a full non-abelian group. And in this geometric engineering picture, you need to, so you have D2 branes on the fiber, you also could wrap D2 branes on the base curve, so you want to decouple the two. That's the so-called 4D limit or geometric engineering limit. And in this picture, then the gauge theory instantons are the Warsche instantons that wrap the fibers. And then in principle, by summing this instanton, you can reproduce the n=2 pre-potential. And in fact, this can be done for you by geometry using mirror symmetry in type 2B, where, so for this kind of setup here, there is a local mirror, which take this form, where it's like a local threefold, which is described as an hypersurface in C4. like u squared plus v squared plus px of y, and px of y equals 0 actually is the celebrated Separator curve that, if you want, solve the low energy physics for you. Then in this picture, you have, of course, BPS particles on the Coulomb range, which are D3 branes wrapped on 3 cycles. And yeah, so in type 2b, it's really a classical picture that gives you the low energy physics. Now, as we could do directly on a Separator curve, we can take further limits. So for SUN engineering, for instance, in SUN Separator curve, we could tune some of the couplings, the parameters, and the Coulomb range parameters to go at Argyll-Douglas fixed point, so an intrinsically superconformal field theory. And when you do that at this level of the geometry, you get this very simple threefold, which is takes this form here. So this kind of singularity then, so this in general is a smooth threefold, but this guy is literally a canonical singularity in type 2b, and it directly engineers a superconformal field theory for you. Okay, so going back to type 2a, well, the geometric engineering, we said we had a 4D gauge theory and we took the 4D limit or the geometric engineering limit, but it was realized already back in the days that this is of course not necessary to a QFT interpretation because we're already on a compact Calabi-Yau, so you already decouple gravity, but the QFT interpretation of the low energy theory of type 2a on this local threefold is not 4-dimensional but 5-dimensional. The interpretation is that you have a 5-dimensional superconformal field theories that is compactified on a finite size circle, when the finite size circle is like essentially the string coupling because it will be the M theory circle. So what happens is that you really have you should really think about the 5D SCFT, which I would call TX 5D, which is defined, if you wish, as the low energy limit of M theory on a canonical singularity X, the threefold. And then if you put that M theory on a circle and so on, you go back to a type 2a and you have the theory on a circle. Now, directly in M theory, we have, again, the same picture as here. You have a threefold like this, but really, we don't need to take a limit between the size of the base curve or the fiber. So they're all on the same footing. I have M2 branes wrapping all of them. And when I take the limit, when everything collapses to a singularity, I have an interesting fixed point. But then I can still take some similar limits when I would now have a 5D gauge theory interpretation. When I have M2 branes that is the W bosons and the M2 branes on the base curve give the so-called instanton particles that can exist in 5D. Now in 5D, all the low energy dynamics on the Coulomb range is again classically computed. No, it's actually classically computed by the M theory geometry. Yeah, so it's just a triple intersection number of some divisors in this threefold after you resolve it. So some general feature of 5D SCFT, beyond the fact that they exist, we don't know that much about them, but there are some general results. So from the geometry, first of all, we can see that, well, yeah, we can see that there are some operators, which are slightly mysterious, but there are real operators that can get VEV, and there is a real Coulomb range. So unlike in 4D, where it's a complex Coulomb range. Those SCFTs have no marginal parameters, but they can have deformations. Here I should cite some important work recently by Cordova, Dimitrescu, and Intralegator. I'm sorry, there might be some oversight in the citation in these slides. So there will be some operator that with a coupling of mass dimension, and then it will flow to some higher physics. And in some interesting cases, we know that it flows to something that can be described as a 5D gauge series. 5D gauge series are just effective low energy effective descriptions, since the gauge coupling is the inverse gauge coupling is a dimension of mass, so it's non-randomizable, but nonetheless, yeah. So the IR is IR3 gauge series description. Moreover, this SCFT will have a Higgs branch, which in general, well, we don't know much about it, but we know for first principle that will be some hyperkähler cone by superconformal invariance of some quaternic dimension dh. And here I'm talking about the quantum Higgs branch, so it's really the Higgs branch that emanates from the fixed point. So we could also do this deformation, go to the gauge theory, then look at the Higgs branch of the gauge theory, but that will be typically not related to the quantum Higgs branch. So to summarize a bit here, from how do we see both this the Coulomb branch and the Higgs branch from the geometry? The Coulomb branch arises in M theory as the space of all Crepant resolution. In fact, we have the extended Coulomb range when we also can turn mass for background vector multiplets for the flavor symmetry. So when you do a Crepin resolution, so you will replace the singularity by a bunch of surfaces, the exceptional divisors, and there will be R of them. And R then is, by definition, from the geometry, the rank of the SCFT, the dimension of the real Coulomb range. There will also be a bunch of curves, which are dual to non-compact divisors, what I call F here. This will be essentially the rank of the flavor group. And so the extended Keller cone, which is, again, classical geometry, gives you everything you need to know about the Coulomb range. On the other hand, the Higgs branch should correspond to deformation of the variety. So you can deform the canonical singularity to a smooth threefold, which will have 3 cycles, many of them in principle, I mean in general. So the deformation theory, it's not known for computed generic case, but we know it very well, at least in 2 cases, for toric deformation and for the hypersurface case, which I will focus on. But now in the deformed case, now you have 3 cycles, so you can wrap Euclidean M2 branes on it, and that will correct. So the dimension of the Higgs branch can be determined by just counting deformation, essentially, but the actual structure of the cone algebraically, and even more the metric on the Coulomb range, will depend on all this M2 brane incident correction. That remains a very hard problem. Okay, so now I will focus from now on isolated singularities, which are hypersurface. So I just have a single equation in C4 with a singularity at the origin. And there are 2 conditions here. One from superconformal invariance, that we want the polynomial that defines this singularity to be quasi-homogeneous. So I will have some scalings, Qi for my 4 coordinates. So so there is a scaling invariance of this equation, and there is a condition that essentially the singularity is Calabi or can arise at the limit of a Calabi. That is the canonical singularity condition. And in fact, such a quasi-homogeneous polynomial, so with this condition, so these isolated singularities have been completely classified by a nice paper, mathematical paper by Stephen Wu and Yu, like 17 years ago, and it's been used quite a lot in physics by several people, including Shai and Yao. And so we have a full classification here. I'll just give a bunch of examples. Of course, the simplest example, but maybe to keep in mind, is just the conifold. It also engineers a 5D SCFT, but a trivial one, which is the free hypermultiplet. But if you engineer, for instance, this particular, if you take this particular hypersurface instead, you get a rank 1 5D SCFT, which has an E6 symmetry, which was discovered by one of the first SCFT discovered by Seiberg. Okay, so now for hypersurface singularities, the whole deformation theory is completely well understood. There is a lot of information in this slide, I realize, but actually I don't need that much of it. Let me just say that all we're doing really is we have a f equals 0, which is singular. We just add a bunch of other terms that will make the equation smooth. So you have a smooth hypersurface. And all the monomial that we can add here are just elements of the so-called Milnor ring, defined as follows, just the ring of polynomial divided by the ideal, which are all the derivatives of f. Now, these elements in the Milnor ring are graded by the scaling charge, the Q charge. You can order them, and that's the so-called spectrum of the singularity. It encodes a lot of information about the singularity. I will mention some of it, I guess, later. But in particular, there is a natural Monod-Romy operator that acts on the third cohomology of this singularity. So this, I should mention that this deformed singularity are just the homotopy type. It's a famous result by Milnor. They have a homotopy type of a bouquet of 3 spheres. So they have only compact 3 cycles and no other compact cycles for purpose. So from this spectrum, we know a lot of it, including the so-called Monod-Romy operators. All we need to know here is that there is then a natural stratification of those monomial with respect to their scaling dimension, essentially. And for the one that has scaling dimensions smaller or larger than 1, they will define an element which is called a mixed out structure of type 1, 2, and 2, 1. So those are like similar to the ordinary complex structure deformation that we know in compact Calabios. On the other hand, for the one which have exactly spectral number L equal 1, the scaling weight L equal 1 here, the scaling weight is defined here. Detail don't matter too much, but there is this L equal 1, then those correspond to 3 cycles, so those one are 3 cycles, 1, 2, and 2, and are 3 cycles that are paired to each other. They are dual to each other. while those 3 cycles that sit in this mixed Hodge structure will be unpaired. Okay, so there will be f of them, of the unpaired cycles, and the number of paired 3 cycles I will denote by r hat. I used the letter f a moment ago to define the number of the divisor class number here in the resolution. Here we are looking at the deformation, but the two are related. You can think of it as that for any of these unpaired 3 cycles, you could take a limit when you shrink it to 0, go through the full singularity, and then go on the other side when you have an unpaired 2 cycles. So it's like a conical transition. Now the quaternionic dimension of the Higgs branch is just the number of, well, naively you think in 11 dimensions supergravity, you have hypermultiplets from 3 cycles, so you just count the 3 cycles. More precisely, some of them, depending on their scaling dimension, will correspond to dynamical or non-dynamical fields, so to dimension on the Higgs branch are actually irrelevant couplings. So the ones that do correspond to the Higgs branch are precisely the one from H12 and H22, so R hat plus F. So from the spectrum of singularity, then we compute the dimension of the 5D Higgs branch. And this is, I mean, the analysis of which is dynamical or not goes on to the work of Gugova and Witten 20 years ago. So from this, we just know the Higgs branch dimension from this SCFT engineer at this singularity. We don't know the algebraic structure or the metric. And so what one of the motivation here is to know a little bit more about this Higgs branch. In particular, is it non-trivial or is it just some, for instance, the conifold, after all the incident correction, it should be just a flat Higgs branch because it's a free theory. Okay. On the other hand, we can also compute, given the singularity, we can compute discrepant resolution, which will go on the Coulomb branch, and we can again do that very systematically. It's something that goes back to, of course, the work of Reid, and one of Reid's former student, Guy Barr, actually did a very nice analysis in his PhD thesis 20 years ago about this kind of resolution and what are in particular their topology. So when you resolve, you will have, as we said, R 4 cycles, R plus F 2 cycles, but in general, you might also have 3 cycles in the resolution. That will come from the fact that the exceptional divisors will generally be a rolled surface. And from each, when you have a higher genus larger than 0 curve in the base of some exceptional divisor, you will actually get, for each such sigma g, you will get 2g 3 cycle in the full resolution. Moreover, even if you try to do the maximal crepant resolution, at the end of the process, you might still be left over with some terminal singularities, some residual terminal singularities that you cannot resolve further. So the physics interpretation of this is that you go on the Coulomb branch, but you could also have 3 cycles, so those give additional free hypers on the Coulomb branch. And then if you have still terminal singularities, you actually should have some IR SCFT left over on the 5D Coulomb branch, and that's what I will discuss at the very end of the talk. So what's the view from type 2b with the same hypersurface singularity? So the local Calabi 3, as we mentioned in the case at the very beginning, provides for us a very nice example of Seyler-Witten curves. So in general, it does not look like a curve. It's just like there are 3 cycles and so on. So but it's still a Seyler-Witten geometry. And okay, so let me not explain too much of this, except that, yeah, so this is like the Seyler-Witten geometry. There is a U-plane here. I mean, in general, there are more complicated Higgs branch, but here is like the U-plane for the higher dimensional Coulomb branch scaling dimension, the highest scaling dimension. At the origin of this U-plane, there will be the SCFT, and that's like the singular, well, sorry, at the origin, yeah. At the origin, yeah, there is a SCFT, which is like the singular Calabi threefold. And then when you deform, you get a smooth Calabi threefold, and you can compute everything you need to know, like about the SL2 and SL2 R hat Z bundle over it. So the Seyler-Witten geometry. So of course, we have many examples of that. We could take any quasi-homogeneous singularities, but some of them have been particularly well studied. Of course, if I just take the case where I have x1 squared plus x2 squared plus a 2, this fg, where fg is of type A, D, or E, like this, then I would just engineer an ordinary Argyres de Glace theory of type AD or E. There is some nice generalization of that from Cecotti, Nensky, and Vafa when you have this threefold, which looks like it's of so-called type GG prime. But of course, we can do any other. That's been studied in some paper, including by Cecotti, Del Zotto, Cecotti, Xie, and Yao, and many others. You can take any singularity you like and just compute the spectrum and try to study everything you can. In fact, from this picture here, you really know everything you need to know about the low energy effective action. Okay, so now let's do the same as we did in 5D. Look at both the deformation and the resolution and what they correspond to in terms of the physics. So first of all, the Coulomb range, as we said, is the space of deformation of the singularity in type 2B. And we have the same mixed structure element that now will be interpreted as, so we have this scaling weights that up to this redefinition this can be written as delta L. And those will be literally the scaling dimension of the Coulomb range operators. So you can compute the Coulomb range spectrum directly from the singularity. By some important work by Schapper and Tachikawa, similarly, you can actually, from the spectrum itself, you can extract the conformal anomaly A and C. And all of this is done in type 2B as a classical geometry computation. On the Higgs branch side, we need to consider now the Crepant resolution of this. And that will give you sorry, that's a typo, it should be the 4D Higgs branch here. So that will be the 4D Higgs branch is the space of all Crepant resolution. You will have one hypermultiplet for each 2 cycle in the resolution. So that gives you, by counting the two cycle, we said it was R plus F. So that will be DH hat, that's the quadratic dimension of the 4-dimensional Higgs branch. In addition, we said that when you do resolve in general, you might have 3 cycles in the exceptional that comes from the exceptional locus. Those compact 3 cycles in the resolved singularity will give rise to 3 vectors now in type 2B. So that's more familiar in 4D n equal 2 theories. On the Higgs branch, you might have additional degrees of freedom. Here you could have 3 vectors, and in addition, if I have still residual singularities, after I resolve, I still have some residual singularities, those should be interpreted as IR SCFTs, so additional 4D SCFT, which themselves have no Higgs branch, but sit there at every point on the Higgs branch of the larger theory. So that matches, in fact, the non-structure of the Higgs branch for many RD residual theories, and with this technique, you can compute that for any of these hypersurface singularities. This kind of general structure of the Higgs branch has been explored, for instance, recently in some nice paper by Beam and Meneghelli and Rastelli, where they look at this kind of general structure of the Higgs branch from the VOA perspective. Now, as we said, this at least from this just classical analysis, we determine this basic feature of the Higgs branch, but the more detailed information, including the Higgs branch metric, is again beyond reach, because now I have 2 and 4 cycles, so I can wrap D1 and D3 Brane instantons on them, and that will correct the metric and so on. But nonetheless, this classical analysis of the resolution gives us some nice general information. The one nice things to comment, and it's like a nice consistency checks on this whole picture, is that we have anomaly matching on the Higgs branch. So on the Higgs branch, the U1R superconformal R symmetry is unbroken. So the Higgs branch, you break SU2R, but not U1R in 4D. So the U1R symmetry can be computed in the CFT as a 24C minus A of the conformal anomaly, which we said can be computed from the spectrum here. And on the other side, on the Higgs branch, we should just map to the low energy degrees of freedom on the Higgs branch. So we have DH hypermultiplet, which contribute this to 24C minus A, or to the trace of U1 anomaly. And similarly, there will be 1/2 B3 vector multiplet that contribute this factor. And the last factor is from the residual singularity, since I could still have residual IR SCFT on the Higgs branch. So the UV computation on the left and the IR computation have to match, and that's a nice check of the geometric picture, because from the geometry you compute other different objects and they have to match. I mean, I don't know if that is like if there is a general geometric proof of that. I haven't seen that. Okay, so a last piece of information that we can extract quite easily from this geometry, let's say for this 4D SCFT in type 2B, are its higher form symmetries. And in this case, the only thing you can have for this class of hypersurface are one form symmetries that you can see as going again on the Coulomb branch of the theory by looking at line defects on this that can be charged under a putative one symmetry group. And this one form symmetry will be spontaneously broken. So how it happens essentially that you can have D3 branes that now are wrapping some of the non-compact tricycle, relative tricycle that can end on torsion cycle on the boundary. So in general, the boundary of this singularity, or the boundary of the deformed singularity, will be the so-called link of the singularity. It's a nice 5 manifold whose topology is very well understood. So in particular, it can have torsion in this second homology, which always takes the form of F plus F. So that's, yeah. So that will be the so-called defect group that has been called defect group in various contexts in recent literature. We heard some of that in the talk of Dupay on Wednesday. And then by taking some Lagrangian sublattice of this, you can look at all the possible global structure of the 4D SCFT. So you will choose a sublattice F, for instance, a single one that corresponds to, yeah, well, you can choose any sublattice you want, and that will be what we'll call one electric or magnetic one form symmetries and so on in those theories. So here is just an example for DG prime theory. Well, you can just compute this torsion group, and then that's the result for F here. We'll give a concrete example in a second. Okay, so finally, I would like to connect those two. So we took the same singularity and we reminded ourselves, or we developed a bit of what can be known, the general picture of the Higgs branch and the Coulomb branch in 5D in M theory, or in 4D in type 2B. So they are connected schematically like this. It's pretty simple. Let me go through that. So the basic picture is that, of course, the system in M theory and in type 2B are completely different SCFTs, they're in different dimension and so on. But we know how to relate those things. So in M theory, we just first reduce on a circle. We get this KK theory, as we said, in type 2A. But you can reduce it further at type 2A on a further circle, and you would get, well, whatever you get. So I will call that again a KK theory with 3. The only thing that we know in general is that we have 3D n equal 4 supersymmetry, because that's what we started with, H supercharges. So that will be a KK theory. That will, on a finite size circle in type 2A. Yeah. Now, below the KK scales, I can just think of it as a 3D supersymmetric QFT, maybe with a cutoff, that I will call this electric quiver 5, EQ5. But in some nice circumstance, you can then remove the cutoff by just describing this EQ5 as some, for instance, gauge theory. That will be then what is typically called quiver theories in 3D. Similarly, in type 2B, we reduce on a circle. On a finite size circle, we flow to the IR. Anyway, below the KK scale, then we have this description as this electric quiver of the 4D theory, what I call EQ4. For not to confuse with the fact that they might not be actually quiver gauge theory, in the paper we call them electric quiverines. So either in 5D or in 4D. Now, what we also know is that once you come back around a circle of radius beta or 1 over beta, they're related by T duality. So the two pictures should really be related by T duality. In fact, it's known from the work of Ori, Oguri, and Vafa that this kind of T duality in this essentially this setup realizes perturbatively in string theory the famous 3D mirror symmetry of interrogator and Cyber for 3D n equal 4 theories. So the relation, that's the relation up to an important subtlety. So the subtlety is as follows. Let me first define the magnetic quiver of the 5D theory as the 3D mirror of the electric quiver 5. Similarly, the magnetic quiver of the 4D theory is the 3D mirror of the electric quiver 4. And by this picture, you would think that the electric quiver of 1 is the both electric quiver 4 and 5 are related by mirror symmetry. It's almost the case. The subtlety has to do with those unpaired 3 cycle or 2 cycles. So that correspond to flavor symmetries of these theories. So the proposed relation is that the magnetic quiver of the 5D theory is obtained by taking the electric quiver of the 4D theory here in type 2B, and then gauging the U1F symmetry that came along the flow. And similarly, for the magnetic quiver of the 4D theory, you take the electric quiver of the 5D theory, and so those are all 3D theory, right? But the electric quiver 5 and gauge the U1F. This gauging is of an abelian symmetry is this so-called S-type gauging that was discovered by Kapusin and Strassler and further studied by Witten. And it's a very simple and nice process in 3D. In particular, it is reversible. So you add, you gauge an abelian symmetry. You add, you add the theory, but you also add, when you do that, you also add a topological symmetry, and you can keep track of that. And then you could also gauge the topological symmetry in the new theory, and you go back essentially to where you started. So this is a reversible process. Okay. So that's then to summarize. Of course, in 3D n = 4, the Coulomb branch and Higgs branch are now both hyperkähler cones. So the Higgs branch was always hyperkähler cones, and the picture we have is that we don't expect the Higgs branch to change when the dimension reduce. So it's the same. The Higgs branch of the 5D theory is the same as the Higgs branch of the electric quiver. 5, in particular, it has this dimension dh. But the Coulomb branch was really in 5D, but it becomes again quaternionic. I mean hyperkähler. I mean in 3 dimensions. And of course, mirror symmetry exchanges the two. That's the general picture of just their dimension. So what we're doing here is, what was, if you want, the motivation is to use this beautiful context of the magnetic quiver that was advocated in particular by, well, starting in the work early in the 90s of Anani and Witten, and a lot of recent work by Anani and collaborators. When in their case, they look at PQWebs systems of various SCFTs in 4D and 5D, and do various operations to extract from this a 3D n = 4 gauge theory, whose Coulomb branch is precisely the Higgs branch of the quantum Higgs branch of the theory you wanted to start with. So those are typically brainwave operation and so on. Here we propose a way of getting the magnetic quiver, as a matter of principle at least, from this geometric engineering picture. So in summary, in particular, if I want to know the Higgs branch of the 5D SCFT, I need to compute the magnetic quiver of this 5D and compute this Higgs branch, and similarly for the 4D SCFT. Okay, and the one advantage of this picture is that, unlike I told you that the Higgs branch in 5D and 4D in M theory and type 2B was pretty hard to get handled because of this M-brane or M2 brane or D-brane instanton. Similarly, now in this picture, we still have some instanton corrections in those 3D, but when you just think about in terms of 3D gauge theory, or well, 3D theories, yeah, gauge theories, you have a better handle in it because this problem of summing the instanton comes about to summing monopole operators in 3D, which are much better understood. So after all of this, I think I have 6 minutes. Perfect to discuss examples. So the first example will be this singularity here. So x to the 2, x2 to the 3, x3 to the 6, x4 to the 6n, where n is some integer, 1 or larger. So this for n = 1 in particular is the famous E8 theory of Seiberg, and in general it's a rank n generalization. We can compute all the things we said, the resolution, the crescent resolution, and the deformation, and so on, and compute all the various data, R and F and R hat of these singularities. In particular, if you look at the crescent resolution, you will have R exceptional divisors. One of them will be dp8, and the n-1 others will be ruled surface over genus 1 curves. So in particular, there will be 2 n-2 3 cycles in this particular resolution. By checking the intersection numbers between all these divisors, you can match to the 5D gauge theory, something in that case that was done by integrator Morrison and Seiberg in '97. And in that case, the description of this particular resolution is in terms of the low energy description in terms of a 5D gauge theory, which has an SPN gauge group with 7 flavor, fundamental flavor, and 1 anti-symmetric. Okay, on the deformation side, we compute again the spectrum, let's say in terms of those 4D delta, which the deltas here, the scaling dimension on the 4D Coulomb branch are all integers. And well, in that case, it's again a well-known case. but you can see that it's only the only way to match it to the spectrum of Coulomb range. You can match it to Lagrangian SCFT, which is just a bunch of SUN gauge groups pictured by this quiver, which are connected together by bifundamentals. And all the beta function vanish, so it's a nice Lagrangian SCFT. So in our case, then it's a Lagrangian theory, so actually reducing here on our picture directly to 3D can be done directly. I mean, it just what you should have is that the 3D theory can be described by the same SUN type gauge theory as a 3D n=4 theory. Now, these are SUN gauge group, and there is a U1 to the 8, so F was 8 here. The U1 to the 8 flavor symmetry, which is the flavor symmetry that rotates the hypers here, can be gauged, and then all this is the same quiver that you get, but it's in terms of U1 gauge group, and this will be our magnetic quiver of the 5D theory. Okay, so that connects to known results. Now, for something new, you take the following singularity, which is in type 2b, it's well known. It engineers a Argyll-Glass theory or a Chekhoty-Inaitsky-Vafa type theory of type A2D4. I show here the information. In particular, there is a nice spectrum of this simple spectrum of 4 Coulomb range operators. In that case, you can think of this, you can describe this Argyll-Glass theory as a conformal gauging of an SU2 with A3 type Argyll-Glass theories. And there is a choice of a global structure that has to do with the one-form symmetry that I mentioned before. In that case, you can think of it as being the usual form global structure of an SU2 gauge group in 3 dimensions, except that we have this kind of non-Lagrangian matter. And I mean, that's a prediction from geometry that this Lagrangian matter A3 here coupled to this SU2 in a conformal way. This A3 has a SU2 global symmetry. You can couple it to this SU2 gauge theory. And the prediction then from the geometry is that since we see a one-form symmetry, this kind of matter should not break the center. Okay, so that's in type 2b. Nothing mysterious there, just interesting model. But if you look at the same model in M theory, it's a bit more mysterious. So first of all, it is known that, again, we need to not take, so in that case, F equals 0. So I can just consider that now as the magnetic quiver of the 5D theory. Well, first I need to reduce to 3D, and then that will be the magnetic quiver. So that, let me reduce that to 3D. Well, we can use the fact that the A3 theory is known that it flows to 3D. I mean, it can be described, it flows to a fixed point in 3D. That is the fixed point of 3D SQED with 2 flavor. So U1 with 2 flavor. So I replace my A3 here with essentially a U1 with 2 flavor, that's the SU2. So that's the gauge theory description of my electric quiver, which is the same as my magnetic quiver of the 5D theory. And then the structure of this Higgs branch can be obtained by using, I mean, as a diagnostic to see at least how it looks like. You can compute this Hilbert series, which is like the simplest partition function for these theories that you can compute. And there is a nice formula.
Just to let you know, you just got 1 minute left.
Okay, thanks. So there is using the numerical formula, you can see that the Higgs branch is non-trivial. In one case, it is like 3 hypers. In the other case, it is like a quotient of 3 hyper. So that leads us a notative conjecture that, and other example, that if you look at these singularities and look at them in M theory, that will correspond to 3 hypers or discrete gauging from them. I mean, it looks very non-trivial from M theory, but that's what our picture suggests. Very quickly, similarly, you can consider more general singularities like this one. This one is one example when there is still a terminal singularity. And terminal singularity is precisely the singularity we discuss here. So this is an example, again, nothing mysterious in 4D, in type 2b, but in M theory, it looks like a new rank 1 theory that is not in the list or in the classification that have been proposed so far. So that lets me to conclude. So we revisited the geometric engineering of 4D and 5D SCFTs at hypersurface singularities. And most of the mathematics, I mean, all of the mathematics is really classical. There'll be some nice results 20 years ago, but most of the math about those things is known since the late 70s. Nonetheless, we see that by doing all this resolution and deformation very explicitly, you could uncover some new physics. The analysis captures essential feature of both the Coulomb branch and the Higgs branch, as we saw. And to explore the Higgs branch physics, we then reduced to 3D and related the 2 theories by a mirror symmetry. So this is, I mean, we had the paper today, but it's also, there will be more to appear and more work in progress. I think there is many more to be uncovered. So stay tuned. I would like to conclude with like maybe two questions. First is, can we really understand those? So I just told you that there are various, well, very fast, I told you that there are new rank 0 5D SCFTs. Many of them, or maybe all of them, seems to be just discrete gauging of free hypermultiplet in 5D, although that's not approved yet. It looks like free hypers in 3D, but it could be non-trivial in 5D, more non-trivial. In any case, it will be very interesting to understand that better in QFT language, because once you start putting those rank 0 building blocks together in rank 1 theory and so on, it seems to give many more possibilities as to 5D physics. And as a aside, I would like to mention something maybe more for the experts, that in all this construction, I was really, I mean, under the hood, we were thinking about either supergravity approximation or plus incident corrections, but really a lot of those singularities actually do not admit redshift flat conical metric. That's true, for instance, for the one that gives Argyll's theory in type 2b. So it's known that there is no like Sassagenschen metric on the link. And I don't know what that means for string theory, but that's an open question. So thank you, and yeah.
Thank you very much, Cyril. I'm going to unmute everyone and invite them to give you a round of applause. Very much for a nice talk. And I'll now open up the floor to questions if anyone has any questions. You can use the raise hand feature if you like, or you can just unmute yourself if you prefer. Okay, Shlomo Razamat has a question, so I'm just going to unmute you. Please go ahead.
Hi, Cyril. Thank you for the talk. On one of your last slides, when you showed the last of your example, I think, the slide before. Yes, no, the next one, sorry.
Yeah.
So is it the mirror dual of the T2 theory?
Yes, I believe so. Yeah.
So is there a meaning? So it's in your picture for that? So in that case, I think there is the theory on the left is just a discrete gauging of a free theory, right?
Yeah.
So do you have a?
That's what the adversaries seem to say. Yeah. So I mean, it's a bit subtle, but it seems to be the singularity is like can be. What was it? Yeah, the singularity can be deformed to like the theory description of the 5D T2 theory, for instance, by adding some marginal terms.
I see. Okay. Thank you.
Okay, there's a question from Michelle Del Zotto. So I'm just going to unmute you. You go ahead.
Hi, Cyril. Thanks for the very nice talk. So I have a couple of questions, if I may. So the first one is, can you go one slide after this? Yes, can you speak about this?
Well, yes. So yeah, I should have shown the resolution, but so yeah, you can. Well, what do you want to know about it? I mean, I can speak more about it.
Why is it new? What is?
Yes. So if you compute this information here, you see that there is no flavor rank. Apparent at least. It's a rank 1 theory because it has a single resolution, but not the it has terminal singularity still. So you cannot resolve further that. If you compute the deformation and so on, you see that the dimension of the Higgs branch is 16, which is not the number of the dimension of any rank 1 theory that is known. So yeah, it looks like, and okay, so on the other end, the exceptional divisor looks in that case like DP6, but with a singular exceptional divisor, like a singular DP6. So it looks very much like the E6 rank 1 E6 theory, but coupled to something else, which is this kind of residual singularity.
And do you have an interpretation for this residual singularity? Is it some sort of generalized matter? Or?
Yeah, I mean, that's what the residual singularity is. The one, it's like the T2 here.
Mm-hmm.
I mean, it looks like T2, but yeah, I mean, it is T2, but I don't know if T2 in 5D is, well, it's a free hyper or something else.
Yes, because the
like
idea was that
the
idea was that the classification of rank 1 theories, right, is based on, or at least the historical one, is essentially based on studying gauge theories,
yes.
coupled to ordinary matter and check properties of the metric along the Coulomb branch.
Yeah, so the logic is that instead we're taking the canonical singularity seriously, and we see all this canonical singularity. Like the point, but one of the point I want to make is that the same interpretation of this thing, the same singularity in type 2b is completely mundane. I have a SCFT with an X branch with an extra SCFT on top of the X branch is well known.
Yes.
I mean, example of that. But here in M theory, then you have to interpret this residual singularity, and yeah, the interpretation would be as no SCFT everywhere on the Coulomb branch of the 5D SCFT.
And then the other question was if you can, you mentioned this idea of ranked 0 CFTs in 5D. And can you comment about the same question about 4-dimensional theories?
Yeah, we have some brief comment on that. I mean, you don't have that. You can have play the same game for different type of singularities. If you look at toric singularities, toric singularities again engineer things like the E1 cyber theory in 5D very nicely in M theory as a isolated singularity. If you consider them in 2B instead, they look like interesting rank 0 SCFT. That's something that was mentioned in some paper already by Xie and Yao, I think like a few years ago. Although they didn't really study much, and it's really hard to study anything about it. But yeah, from the same kind of computation, at least using the magnetic quiver, in the case of like, for instance, the E1 toric singularity, it looks like, again, I think in that case, like 2 hypermultiplets with possibly a Z2 gauging. So there is a choice of global structure in that case as well.
So also in that case, they have like discrete gaugings of a bunch of hypermultiplets.
Well, what we can do is go reduce to 3D, compute the X branch. You know, we compute the X branch by going to 3D. So in 3D, it looks like the fixed point is just 3 hypers, but it doesn't tell you that much about 4D. I mean, we know also that the mirror dual of Argyle theories in many cases are 3 hypers and so on. There's been recent work to that effect. That doesn't mean that the Argyle theory upstairs was non-trivial. It's not. There is a lot of, essentially, because a lot of those dimensions on the Coulomb branch in 4D, we know flow and so on once you reduce on the circle, right? So.
Yes. Okay, thank you. Very, very interesting. Thank you.
Okay, are there any other questions? Okay, it doesn't look like there are any more questions. Oh, no, okay, there's one more question. I'm just going to unmute you so you can ask your question.
Hi, thank you. It's just a technical definition. It's just a technical question about the definition of your mixed Hodge structure. Are you using the Delignier's definition or for mixed Hodge structures on singular varieties here? And if yes, what is the weight filtration?
Yes. It is, and the weight filtration is just defined by given from this number. So those number here, or more precisely, the exponential of this number e to the 2 pi I of this Li are the eigenvalues of the monodromy operator, the classical monodromy of these singularities. And in those cases, for this quasi-dimensional singularity, it's a diagonalizable monodromy and so on. So you have very simple weight filtration, but yeah, that's what it is.
Wait, the monodromy should be quasi-unipotent.
Yeah, but in that case, it's unipotent. And so
okay.
maybe I wrote
it's
it.
just given. Okay. So you're calculating the mixed Hodge structure essentially using the Picard-Lefschetz theory or knowing the monodromy around.
Yeah, exactly.
Okay. Thanks.
Yeah. Any other questions for Cyril? Okay. Okay, if not, let's thank you again, Cyril, and I guess we'll go and have a break now until the next speaker.
Thank you.
Thank you very much, everyone.